Okay, hello, everybody. Hey, Gemma. How you doing, Gemma? Good timing. How are you doing? I hope you're doing really well, Gemma. I was watching some football this afternoon. That's what I was doing. Watching it coming home. Now we got a final on, I believe, Sunday, right? This is gonna be exciting. England and Italy. Oof. It's the two powerhouse countries. It could be better. Really? Everything okay? I hope everything's okay. Want to be sure that you're taken care of at least, or at least people are treating you well. It's kind of important, you know. But hopefully work's not too crazy. Oh, that's kind of a bummer to hear, Gemma. You think you can make it better, or at least change the situation? Or is work kind of getting to you a little bit because it's just kind of eh? Or hopefully that guy has left you. So just kind of thinking about that too. Your what's that guy? Ex-boyfriend. That's right. Like trying to think of like what's that term again? Honestly, if I could, I would, but I can't. Yeah, I know. Some jobs, admittingly, Gemma, some jobs you have to begrudgingly do because you need the money for that period of time until you can get something better. That's what you're after at the end of the day. That job is a temporary stepping stone to doing something even bigger and better later on. So I've done a lot of jobs in the past, and some of them not so great. Let me be honest with you. But you know what? It's fine. It's coming home. That's correct, Aiken. It's coming home. I'm doing great, my friend. How are you? It's not even your job? Oh no. Well, if your job's like kind of what's going on then? Great. Oh, wonderful. Wonderful. I'll be starting class fairly soon, but I'm not sure if anybody else is here yet, so I'll just wait for them to pop on in. I know, I watched the whole match. Okay, no problem, Gemma. If you want to keep it private, I totally understand that. The announcers were so biased, but it was so funny just to watch. No, you don't have to, Gemma. No. Anything personal, completely understand. You don't have to say it on the stream. You have a right to privacy at any time. Sterling was diving. Is there still? Yeah, this is the second contact. The Sterling, he got hit on the hip on the way down. It's still a foul. He just dives. Okay, Harry Kane dives. Everybody dives. But the second bump was a foul. Yeah, when they hit hip to hip, I think that was a foul. So it's a light foul, but it's in the box, and then that's what it is. Yeah, the second guy. It's not a card-worthy foul. But you know what? In that moment in time, you got to do what you got to do. So, I mean, as much as we hate flopping, you got to do it because that's part of the game. So, Emma, hello! Emma, how we doing today? Are we doing good today, Emma? Schmeichel's dad was devastated? Oh, man. You know what? The first goal you can't even put on Schmeichel. That goal was impossible. Okay, literally impossible. That was such a good cross into the middle of the box. There's no way that if Denmark missed it, then Sterling would have put it in the back of the net easy. Yeah, because we're trying. Okay, look. Okay, let me be frank here. Richarlison does it all the time. Okay, he doesn't like push guys off. It's like any time you give him a love tap, he dives. Okay, Sterling on the other hand at least pushes through guys and dives when he needs to, but he doesn't dive every single time like Richarlison. Okay, there is a difference, Aiken. There's a difference. Okay, that is why Raheem Sterling is on the national team. Okay, why Richarlison will not touch Sterling in terms of class. I'm just saying. I'm doing great, Emma. I'm doing absolutely fantastic. I hope you're doing good as well. It's true! Go and watch Richarlison with the ball. Yes, I know, but go watch Richarlison with the ball, okay? Watch when he plays for Everton. It's abysmal. He's a great player, but you gotta stop flopping. Like he flops every time he touches the ball. It's terrible. Nah, Grealish was fine. Grealish is exactly what you want him to do. He was an attacking player, creating chances. Then when they got the goal, you switched to a defensive position, you took Grealish out. That was a great move by Southgate. It's exactly what you wanted to do, and he did it to perfection. You can say he's underwhelming, but his presence there is exactly what you wanted. Like, look, Gareth Southgate had a game plan, and as soon as they scored that goal in extra time, he executed the game plan, took Grealish out, brought in defenseman. Okay, just played back. Absolutely outstanding. It's just Southgate has a plan and he's stuck to it, regardless of what anyone says. Walker needs to keep his hands down, spend half the game with it. Yeah, that's true. You know who played terrible? Harry Maguire played awful. I'm sorry, Harry Maguire was terrible. I'm just gonna say, hey, Lee Wen, hello. Yes, I'm sorry, but Denmark got way too much space on the right wing. Way too much space. They gave him so much purchase on the right wing. Did you not watch that all game? Are you kidding? But yeah, that's true. Shaw shouldn't have kept going up. That's true. I'll give you. I'll concede that point, Aiken. Yeah, that's true. Lee Wen and Emma and Gemma. Emma and Gemma. Look at that. And Aiken. Look at that. We got more people in the chat. There we go. All right. Looks like we're getting ready to go here with some math. 126. But you know what? Yeah, Pickford had some rough moments with some shankerific kicks there out of the box, but you know what? And the one goal that he conceded was a banger. Okay, I'm gonna be honest with you, Aiken. That free kick was a banger. I don't even know how the best goalkeepers in the world can stop stop-up anger like that. I don't think it's even possible. So I'm not even going to blame Pickford for that. That was just an unbelievable free kick. So give Denmark credit. They know how to do set pieces really well. So, but you know what? We won. So there you go. England wins. That's all that matters. Okay. Okay. All right, so we got to get going here, ladies and gentlemen. Let's get going here. If the music is too loud, just let me know, and then I'll turn it down. All right, we got to do some intros here, and then we got stuff to do. All right, let's do this. I gotta clap one more time. Okay, there we go. Okay, let's get started today. Welcome back, everybody, to Wednesday. All right, we're gonna pick up where we left off last time. Okay, last time, ladies and gentlemen, we are going to pick up exactly where we left off last time, which was section 6.2. Now, admittedly, I don't know. Is Nick there? Nick, are you there? Nick, I gotta ask. Okay, Nick, I know last time. I'm gonna speak to you, Nick. Nick, I know last time you absolutely hated my guts because we did integration by parts, and I know you didn't like integration by parts. And so hopefully we're going to clear up some more examples with integration by parts. That's what we're going to start with, okay? So I promise you today will be slightly a bit better, okay? Just slightly a bit better. I have to appeal to Nick first because he's like I swear he's like ready to kill me yesterday. Like, what are you doing? Like, I'm okay, man. All right, sorry, bro. I'm gonna be over here. All right, but we have more problems to do, most certainly. And there's Elizabeth here. I apologize, I'm here. I was on the phone with the vet about one of my. Oh, okay. Well, make sure pet is taken care of. And I know, like I was talking earlier, hey, pets are family. Totally understand that. All right. Okay, ladies and gentlemen, we're going to still keep along with integration by substitution. We're going to do a few more examples here to kind of get more comfortable with integration by substitution. We did a couple of examples here last time, and I want to do more here just to showcase exactly how we're going to approach some of these problems. And some of these problems here are not as clear-cut and dry. So we're going to take it up a notch here for this next example. You'll see exactly how we have to basically kind of compensate stuff out. All right. So let's look at. Oh, there we go. All right. So where's the paint tool here? All right. So we're gonna look specifically here at number. Let's look at number. Yeah, let's look at number 5. Okay. So I'm just gonna start here at number 5. We're gonna work our way up through some examples here. So here we have the integral of x to the third 5x to the 4th plus 6 to the 7th power dx. Okay, so we want to find this particular integral here for this problem. All right, now by itself this isn't like the worst, but I do want to point out here a couple of things. Let's talk about once again what we discussed here yesterday, and again I want you to help me here, guide me through this example, tell me how I would go ahead and approach this particular problem. Okay, so Okay. Now, so last time we had to basically define a u. Okay, since we're doing u substitution here, we had to go ahead and define a u. So yeah, we're still doing u substitution. Nothing's changing in terms of the letter we're using and stuff like that. Again, one of the things we talked about, the big trick here behind u substitution, is we had to kind of look ahead and pick a function for u in which you can substitute everything in terms of u and then take the derivative. Okay, so essentially we want to pick kind of the tougher of the two functions and see if we can, looking ahead here, because as you can see as part of the process here, once again, we define a u and we're going to take the derivative of that thing we call u, and then hopefully we put all the pieces in and replace the integral with everything in terms of u. That's essentially what we're after here. Okay, now this example here is going to reflect that, just with one small twist, but I'll show you what that is here. But why don't you guys help me out here, at least at the very beginning. What should I define u as here in this problem? What do you think would be a good idea I should define u as? Got a couple of choices here, but why don't you guys tell me? What's a good choice for u in this instance? What do you guys think? Choice for you. 5x to the fourth plus 6. Okay, that sounds like a great idea. All right, so I'm just going to take that little inside guy here, and there we go. All right, I quite agree with that. That's fine. You're probably saying, well, how do you agree with that? Well, let's look ahead and see what happens when we do choose 5x to the fourth plus 6, as Lee Wen has stated. Now, remember the next part here, we have to take the derivative of u. So the next part here, we're going to take du. Now, what's du equal to here? What's du equal to here? What's the derivative of 5x to the fourth plus 6? We have here. Derivative of 5x to the fourth, ladies and gentlemen. 20x to the third. Okay. Okay, good. And what do we need to put next to 20x to the third? Let's at least answer that. What needs to go next to 20x to the third once again? So if you look at our steps here on the left, what needs to go next to 20x to the third? dx. Okay, we need to put a dx next to that. Okay, so we took the derivative of x. We need to put a dx next to that there. Okay. So let's start substituting some stuff in. Let's see what we can do there. Okay, no problem, Jim. I will. All right. I promise I'll check out the DMs. All right. Appreciate you. Have a good night. Okay. Aiken, if you're still there, if you're in bed, then have a good night. If you're still here, hey. All right. So let's play a little bit of substitution. So again, we have 5x to the fourth plus 6. I'll put that in black. This guy here is equal to u, right? So we know that for a fact. This is going to be u. That's perfectly fine. So let's put this all in red. So right now, as it stands, I have u. Oops, let me put that in black again. I have u to the 7th power. So that's what I have here so far. But I also need the du part by replacing the x to the third and dx. Well, let's check that out here for just a moment. And here comes the twist in the problem. Okay, let's take a look at what else we have left over. Well, what we have left over is we have a dx, which is fine. We have a dx down here. And we also have an x to the third. Okay, well that's fine too. However, I have an x to the third and dx here. However, what's stopping me in my progress is I have this 20 over here. This 20 is preventing me from having x to the third dx. So what I can do here, in this case, is I can go ahead and I can divide by 20 on both sides. If I divide by 20 on both sides, I can have I can rewrite this as 1 over 20. That's another way of writing over 20 times du equals x to the third dx. Okay, so all this stuff in brown is going to be equivalent to 1/20th times du. Okay, so that's what I'll put over here as well. Okay, before I move forward here, are there any questions about that? Does everybody understand where I got that from? And why I decided to do it that way? Guys, let me know if you have questions, because I remember yesterday it was a pretty rough go, which I totally understand. So again, ask me plenty of questions if you're not sure, okay? It goes for everyone. They understood? Elizabeth, Nick? Think you get it? Okay. We'll be doing another example after this, but want to be sure that it's a little bit crystal clear about where that came from. Again, I try to make things as visual as possible so it's easy to follow along. At least I try anyway. How we doing, Nick? You have any questions there, my friend? All right. Okay. Remember, stop me at any time, Nick. All right, and just keep asking questions. All right. All right. So the one thing that we talked about here when we first talked about basic integrals yesterday is we have a constant here of 1 over 20. What's nice about integrals is that we can take that 1 over 20. We can take that 1 over 20 and we can bring it outside of the integral. Okay, if it's a constant number, we can take that 1 over 20, we can just bring it on the outside of the integral here. The du stays inside because we want that on the inside here, of course. Doesn't make sense to take that out. But the constant number here can be taken out, no problem, just like so. So, what we do is, of course, we go ahead and take the integral here, which is u to the 8th over 8. 1/20th times u to the 8 over 8 plus c. And then we go ahead and finally substitute u back in and combine this 20 and 8. We're going to get u here is 5x to the 4th plus 6. Get 5x to the 4th plus 6 to the 8th power. This is going to be 1 over 160. So 1/160th times 5x to the 4th plus 6 to the 8th power plus c will be our final answer for this problem. Okay, so just a little bit of extra stuff that we did here, but let's enter that in at least for this. So 1 over 160 times 5x to the 4th plus 6. Okay, raise that to 8th plus c. Okay, and we can check that out and see if that is correct. And it is. There you go. All right. Any questions about that problem there? Hopefully that was okay. Eight's not. 7. All right. So I'll let you guys have a pick of the litter here. I am gonna do this one, so I'll have you guys pick the next example. The next example here will be 6, 7, or 9. 9 is kind of nah, but 6, 7, or 9. 8's not a very interesting problem, but 6, 7, or 9. Which one would you guys like to do next? So Elizabeth says 7. Okay. See what the others have to say. You guys could pick 6, 7, or 9. Okay, Lee Wen says 9. Alright, let's see what Emma and Nick have to say. And anyone else in the chat that I'm missing. See what they have to say. Yeah, I'll just let you guys pretty much tell me what to do. 9 works, okay. Could do 9. That's perfectly fine. Okay. Let's do number 9. Let's see how that goes. Okay. Democracy. There you go. Alright. Okay, so number 9 here. Let's do the next one. We have the integral of e to the 5x over 3 plus e to the 5x dx. Okay, so we gotta make a u here. What do you think our u would be? Alright, so you guys have to pick it. What is our u going to be here? Again, you got a couple choices here, but one of them is the clear winner compared to the other. So, what should u equal here in this case? What do you guys think? I'm gonna define that u as in order to do that particular substitution. So, you got two choices here, ladies and gentlemen. You have, of course, e to the 5x, and you have 3 plus e to the 5x. So, you say, well, one of those two have to be what u should equal. What do you guys think? Which one should u equal here in this instance? Tough one, looks like. I promise you there is a winner between those two. How do you know which one we're supposed to choose and set u equal to? That's the trick here, Elizabeth. The trick here, like I said, you need to look at the trick here. You need to look a little bit ahead, okay? So you need to think a bit ahead here. One of the trickiest parts about this concept here, admittingly, Elizabeth, is that how do you know which one to choose? You know, how do you know that that's going to be the choice that I need to kind of go with? Well, that's what this is about, okay? That's what makes this concept especially difficult, is that you do need to look a little bit ahead in the process to see what would work and what does not work. If you try one, you're going to hit a dead end fairly quickly. All right, so one of them you will hit a dead end there very quickly. The other one, you will not hit a dead end. You'll actually be able to solve the problem out. So it's not, like I said, it's not as clear cut as it seems. Okay, it's not super easy to see. That's why I'm going slow over these particular problems. But if you look a little bit ahead, which one would make the problem significantly, think about it this way, which would make the problem significantly easier to do an integral of? You know, So that's maybe another way to kind of look at it. If we define u as a particular function, you're like, okay, how can I, basically take the integral with u in there instead of, this x's and stuff. Which one would make it easier for me to do? Well, you can kind of think of it that way as well. So based off of that, I know it's not the best answer that I could technically give in this situation, but that's basically what I want to tell you is like that's what you kind of need to be looking for here in these problems, right? So if I were to choose between e to the 5x and 3 plus e to the 5x, which one would you choose then, Elizabeth? Which do you think, if you replaced everything with u, would make it significantly easier to do the integral of? That's what I'm asking you guys, okay? That's essentially what I'm asking you here, all right? You either choose one or the other and then see what happens. If you want to do pick and choose, you pick and choose. Okay. So you chose 3 plus e to the 5x, all right? Now I can totally understand that that's a guess. I said, okay, go with it. Let's see what happens. I'm just going to say that. Just see what happens. If you're going to say, I'm not sure, fine. You know what? Just guess, see what happens, all right? I guarantee you one of them you'll end up with a dead end, and the other one you'll end up with an answer, all right? So how about du? What's the derivative of e to the 5x? Or 3 plus e to the 5x, I should say. Sorry. What's that derivative? You guys remember here, the derivative, you have to do the chain rule on e to the 5x. Remember that e to the 5x here? Keep the, you keep the exponent the same, and then you take the derivative of 5x, which is 5. So du here will be 5 e to the 5x dx. Okay? So that's what du here is in this instance. Okay. So let's take stock in what we have here. Okay? I'll show you why this is actually the correct solution here. At least what to substitute. So here you have u. You would go here on the bottom. Okay? This is what you have. You effectively substituted for this guy right here. What do you have left over? What you have left over is everything else, which is e to the 5x dx. That's what you have left over. Well, I have an e to the 5x dx here on the right-hand side of this du. Great. That's what I'm looking for. I do have this roadblock, though, of 5. So I need to divide on 5 of both sides here. So at this moment in time, I have 1/5 du equals e to the 5x dx. Okay, so this is what I have here. Now, admittingly, this looks pretty ugly, but I can rewrite this a little bit easier by taking this 1/5, taking it on the outside. Again, as we talked about here, you can take those constants and then shove them outside since they don't do anything. The du over u here can be rewritten as 1 over u du. You can rewrite that equation just like so. All right. Okay, so can anybody tell me here, what is the integral of 1 over u du? Okay, you guys got to remember your rules here. What is the integral of 1 over u du? So this is a rule we talked about here yesterday. So, yeah, the rule we did talk about here yesterday. So refer to the rules back from yesterday's section. What is the integral of 1 over u du? What's that integral, ladies and gentlemen? What is that integral going to be? I would like to know. Not 1, Li Wen. Sorry. Definitely not 1. We have a special rule for this, Li Wen. I would look back at your notes from yesterday. I would look at 6.1. We talked about integration. We talked about the rules of integration. So if you look back at your rules of integration, I want you to recognize, again, I'm not going to sugarcoat this for you guys. This is stuff that you kind of have to get to know here because, again, you're going to have to do the work for these type of problems. So I will, okay, that's correct. Do recognize here is the natural log of the absolute value, by the way. So, this is the natural log of the absolute value of u plus c. That is correct. That is the integral of the natural log of the 1 over u, sorry. We go ahead and plug in u, which is 3 plus e to the 5x. And then plus c. So if we do this problem here appropriately, you get 1/5. So let's just check it out here. 1/5 times the natural log of 3 plus e to the 5x. And then plus c. I shouldn't have the... There we go. There we are. And let's check that out. Hopefully this accepts the syntax. And it is correct. There you go. All right. All right. Questions about that? Questions? Nope. Okay. All right. Now you're probably wondering, how did I, again, let me reiterate one thing here. Okay. Let me reiterate one thing here. How did I know that I didn't have to use, say, e to the 5x? Okay. So maybe that's a question kind of in the back of your mind. If you tried, let's say you tried it out and you said, okay, you know what? I want to try e to the 5x. Because you're like, okay, you just kind of guessed. You're like, okay. So if I had u is equal to e to the 5x only, this is what you end up with. They're like, okay, let me look at my problem. It has 1 e to the 5x on top and 1 e to the 5x on the bottom. So what you would have is you'd have u over 3 plus u, and then you'd have something in terms of dx. And then you'd be like, well, what do I do with that? And then you begin to realize that the one thing that kind of stands in your way technically is this 3, because you don't know exactly, you don't know what the integral of u over 3 plus u is going to be. I don't even know what that is. All right, that's too, we don't have a rule for that. And no, you can't split it up and cancel u's out if you think you're going to do that. That's not going to happen. You'll run into a roadblock pretty much right away if you go ahead and define u as e to the 5x. So it's not going to work out the way you want it to. And immediately you'll be like, okay, well, that didn't really work in my favor. Let's try the other way with actually just replacing it with the whole thing of 3 plus e to the 5x and then see what I get. So That's essentially what is going on there. All right. So just letting you know exactly how that would work out if I were to try it the other way. All right. Okay. Now the other one I want to do here is this one here, number 10. Number 10 here together. And this one I'll showcase here. Number 10 is notoriously a little bit tough if you don't see it right away, because it's not written that well, but at least I want you to see it for this. So we have x times the natural log of x, and this whole thing is, this natural log of x is taken up to the 5th power, and then we have a dx here on the outside. Okay, so the real question is, of course, is the very beginning. The very beginning we say, all right, well, how are we going to define u? All right, so we define u in this case. Actually, it turns out in this case, to define u, we're going to label that as natural log of x. So you notice what's in the parentheses here. We have something to the 5th power, whatever. Yeah, let's just define it like that. Let's see what we got. All right, so let's take a look here and do du. Now du here is equal to 1 over x dx, just based on the rules here for natural log for the derivative. Let's take a look at the pieces that we have here so far. Okay, so we have this piece here, which is natural log of x. That's going to be u. So let me show you the intermediary step here. Maybe this will be helpful if you can visualize it even further. So basically I start off with a u. I said, okay, I'm just replacing this natural log. That's all I'm doing. So what do I have left over? I have this x I still have here. I have this u to the 5th now. I have u to the 5th, and I still have this dx here. So take a look at what's left over. What I have left over here in this particular case is I have dx, and I have this 1 over x that I have here that I'll circle in purple. Well, what do I do with 1 over x and dx? Oh, well, I can replace all of that with du. Now I could take one extra step here. I still have this 1 over u to the 5th, but all this stuff, this 1 over x dx, all of that magically converts to du. Okay. And so what I do here in this case is, of course, I go ahead and proceed with the rest of the problem, which isn't as hard as it may seem. Again, 1 over u to the 5th is u to the minus 5 du. But the more important part here is how we did this substitution here to get to this point. That's really the big key. Okay, so at least understanding that is going to be the big takeaway. And so here we're going to have u to the minus 4 over minus 4 plus c, our power rule for integration. And then finally, go ahead and finally we go ahead and replace that u. So here we're going to get our final answer. U here was defined as natural log of x. So here we have natural log of x to the negative 4th power over negative 4 plus c. Okay. And we got our final answer. And we can test it out, by the way. So let's put it in. Raise that to minus 4 over minus 4. C. And that's correct. There you go. All right, so we got the right answer. Nice. Okay, there we go. And number 11 is just a two-part. You have to do it in two separate parts. Okay. Any questions about this example here? Hopefully that's not too bad. Okay. Hopefully that's a bit easier to do. Okay, so we got that. Good stuff. All right, so here we got two more word problems here. I'll let you guys pick which word problem you would like me to do. So we could pick number 12 or number 13 as the last problem from this section. So, which problem would you like me to do here? 12 or 13? $13. A 12? Lee Wen says 12. We'll see what Nick has to say. We have 2 votes for 12 and 1 vote for 13. Or if any. All right, so we have 3 votes for 12. All right, so let's do 12 and see what we get. All right. Good stuff. Okay. So, number 12. Number 12 says TV viewers. Okay, TV viewers problem. All right. So the number of viewers of a weekly TV news magazine show introduced in the 2009 season has been increasing at a rate of this function here. A million of viewers in its 10th year on the air, with T being equal to 1, corresponding to 2009. Right? The number of viewers of the program during its first year on the air was given by 6 3/2 to the 2/3 power million. Okay. Find how many viewers were expected in the 2012 season. So, find how many viewers were expected in the 2012 season. So in this case here, of course, if we're looking at 2012, that means that T here will be equal to 2009 is number 1, 10 would be 2, 11 would be 3, and then 12 would be actually 4. So this would be T is equal to 4. I know that's a little strange, but with T equaling 1 and 2009, it actually means that T equals 4 in the 2012 range. Okay, so basically what is this asking us to do? Well, one of the things that we talked about here is we talked about those initial value problems that we discussed here before. This is essentially what it's going to ask us to do again, is these initial value problems. And they give us a value, say, okay, in 2009, they say, all right, if we try this out here, we say, all right, well, f of 1 is equal to this really weird number of 6 to the 3/2 to the 2/3 power. That's essentially what they're giving you here in this particular issue, for this particular problem. Now, the bigger issue is that why they give you this such weird number, like says, you know, 6 times 3 halves to 2/3 power. All right, nobody really says that, you know, in everyday life. So, thing is that, well, how do I go ahead and apply it here in this problem in order to find out what they're asking me for? Well, that's where the integral is going to come into play. I'm going to take the integral here of 2 times 1 plus 1/2 t to the negative 1/3 power. Now remember here, very important, all right, we are going to go ahead and going to see what we get, because at this point, I don't know. All I do know is that if we take the integral here, we'll put dt here, we're just going to use u substitution here in order to go ahead and solve for this particular guy. So let's see what we get, because I don't know. In all honesty, I don't. Now, the more complicated of the two functions is going to be 1 plus 1/2. It's going to take that inside there. 1 plus 1/2 t will be my u. So that's what I have here so far. So what I got here is, again, putting these pieces together, I have this 2 sitting out here. I have u to the negative 1/3 power. I don't have a du yet because I still have some pieces left. Du here is equal to 1/2 dt. Okay, so pretty simple. 1/2 dt is equal to du. So I know that dt, I know that in this case here, what I'll do is I'm going to go ahead and say, well, I still have that piece left over. So I can go ahead and multiply by 2 on both sides. So what I get here is I get 2 du equals dt. So let's see what happens. I have u to the minus 1/3, and then I replace this whole thing with 2 du. I'm going to put 2 du here, just like so. Let's clean this up a little bit. Clean this up here. Here we got 4 u to the minus 1/3, and then we have du. Okay. All right. So far, so good. Okay. Any questions so far up to this point? I hope everybody is okay with how we found that. Is everybody okay with that? No? No questions? Okay. No. Elizabeth or Nick? You guys got any questions so far? Not with the first part? Okay. Just processing what you did and thinking about it. Okay. And if I'm going too fast, just let me know, okay? All right. Now let's take a look at the integral here. All right. So the integral here, we're going to have 4. We're going to have the 4 here. We'll have u. If we add 1 to negative 1/3, that'll be 2/3. And that'll be over 2/3. Okay. And so plus c. All right. So that's what we have here. So if we go ahead and see what we have here, so if we replace, first of all, do 4 divided by 2/3. If you do 4 divided by 2/3, you can do that on a calculator if you want as well. But 4 2/3 flips over because you're dividing by a fraction, so you get 4 times 3, which is 12, plus times divided by 2, which is 6. So if you actually do 4 divided by 2/3, you will get 6 there. And then we can replace u here. U is going to be, where is it? 1 plus 1/2. See. Okay. And that'll be to the 2/3 power. And then plus c. Okay. All right, so this is what we get here in this instance, all right? So now our goal is to go ahead and solve for c. Now, in order for us to solve for c, we're going to go ahead and do the initial value problem here using f of 1 is equal to this gobbledygook of 6 times 3/2 to the 2/3 power. So basically, we're just going to plug in 1 in here for t, and then we're going to see what we get here in order to make it equal. Now, in order to show this off here, I'm going to zoom out a bit so it's easier to see. Everybody can see it on the full screen. So, okay. So what we'll have here is that if we're using f of 1 is equal to 6 times 3/2 to the 2/3 power, let's plug in 1 in for t into this integral, and let's see if we can solve for c. We have f of 1 equals 6 times 1 plus 1/2 times 1 to the 2/3 plus c. So again, let's actually what I should have done here, sorry, I did one thing wrong. Go ahead and just erase this, because this should equal this value here. We have f of 1 should go here, and this should equal 6 to the 3/2 2/3, which should equal this. Okay, so let's see what we get here. So here we get 6 to the 3/2 to the 2/3 power, this really weird looking number. Let's see what we get on the right hand side. So we get 1 plus 1/2, because 1/2 times 1 is a half. 1 plus 1/2 is also 3/2. Plus c. So you can subtract by this whatever looking number is. And yeah, so you're going to come up with a very important conclusion here and why they specifically selected this weird looking number. And the reason is because in this case, 0 is equal to c. So in effect, our constant here is going to be 0. Okay, so we could just take it to the bank here that our function that we should be using here should be just the one we just found in the integral, where we can just drop c off because c is 0. And now all they ask us to do here is to go ahead and go one more step. We want to find out where t is equal to 4, and then we'll be able to have that'll be done after that. So let's see what happens with that. Plug in t is equal to 4 in this problem. Let's see what f of 4 is. 6 times 1 plus 1/2 times 4 to the 2/3 power. This equals 6 times, what is this, 1 plus 2, the 2/3 power. So here we get 6 times 3, the 2/3 power. So this is going to be our final answer for this particular problem for number 12. So let's put this in. And now that we got that down, that there. 6 times 3 to the 2/3 power. Oh. Oh, do I actually need to do it on my calculator? Oh, maybe I do actually. Let's do it on the calculator. All right, let me do this quickly on my calculator. I guess that's what they want. So 6 and 3 to the thirds power. So I get oh, whoop, that was. Oh, here we go. How many decimal places do they want? 1 decimal place? Okay. So I got 12.5. I got 12.5 million with 6 times 3 to the 2/3 power. So let's check it out and see if that's the case here. And that's correct. There we go. Okay. That's the second half of that problem there in that case. Are there any questions about that one? Now that one's a little bit of a toughie. I get the integer. So you get the, are you talking about the 6 there, Nick? So you understand where we get the 6 from, right? You don't know how the numbers were plugged back in. So basically all I did was plug in, I plugged in 4 in for t, because they asked us for 2012, and t equals 4 represents 2012. So I plugged in t into right, let me put it in, I plugged t right here. That's where the 4 came from, where I plugged in the 4. If that's the question about where I put that number in this function, that's where I put the number in. So, because this was t, and then it goes exactly where that t should go. Okay. I know that was maybe a little tough to see, so that's a fair question. So hopefully that cleared that up. Any other questions before I move forward? Any other questions? Or if you need me to clarify further, Nick, just let me know, okay? Okay. Okay. Okay, so let's go ahead and, all right, so that is the end of section 6.2. Okay, I know that's the tough section there. Hopefully the next couple of sections won't be as bad. Okay, those are actually much more doable in my estimation. But we'll get there in just a second. But let me ask here, because I didn't ask yesterday, but I have to ask today nonetheless. But would you like to take a 5-10 minute break, or would you like to keep going? So 5-10 minute break or keep going. What would you guys like to do? Okay, that's fair. Of course. Of course. That's why I'm asking. So, all right. So let's take a break here. We'll come back at 7:15. Okay, 7:15. We'll come back. All right. We'll be back here at 7:15. Let's take a small break. Let's process it. Do what you need to do. We'll be back in 10 minutes. All right. All right. We'll be right back. All right, everybody. Let's get back to it. All right, welcome back, everybody. Get to the second half here. Hopefully, everybody is clear and present. All right, we're gonna get to the second half here, so no problemo. Okay, so we're gonna be doing the next couple of sections here. We have four. I know we have 35 minutes left, but we'll begin at least the next section and a half done for sure, because the next section here is a very, very, very short. Okay, I mean very short. So because we'll talk, and then it'll lead into the next following section after that. So that's what's going to be going on there. So let's go to the big board here. All right. So what we're going to be doing next here, if you see here on the screen, is that the next section here, section 6.3, deals. There's only 3 problems in the homework, by the way, for section 6.3, and there's a reason why. Is because what we're trying to find here is we're trying to find the area underneath the curve. Now, in order to find the area underneath the curve, we're going to look at 2 different methods. One method in this section, which is the approximate method, so kind of like the ballpark estimate. And then we'll look at find out in the next section how to find the exact value behind that. So I want to obviously focus on more of the exact value behind that, but I gave a couple problems here about how you would do it on a more ballpark estimate type of level. Now to do that here, let's look at question number 1 on the handout here. It says, how do we define the area underneath the curve for a definite integral using rectangles? So the way you want to find the area underneath the curve is that you can use rectangles. Now rectangles here are fairly simple to find the area for because of the fact that, well, it's easy to find the area of a rectangle. That's just the base times the height. That's about it. However, what we want to do is we're going to take multiple of these rectangles, and so we want to find the areas of each of those rectangles depending on what curve we're given, and then find the area once we add all those up together. So the question is, how do you do that? Because it seems like it's pretty weird. So let's take a look at this one here. So we said if we have an interval from A to B, so we're going to be now dealing with a very closed interval. We're going to go from one number to another number. Okay, so like 1 to 5, 7 to 9, whatever you want. Okay, so if we have an interval here from A to B and n subintervals, so we're going to be like saying, okay, we want to take n subintervals, which is going to define how many rectangles we want to actually try. Then the area underneath the curve will be equal to b minus a over n, and I'll explain what that is in just a second, times f of x1 plus f of x2 plus f of xn, plus dot 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 f of xn, where x1 to xn are arbitrary points in the n subintervals of equal width. It's important to note that each one of these rectangles should be of equal width at the end of the day. Okay, so otherwise you're not allowed to do that. Okay. All right, now you're saying, hold up. It's a lot of letters. Okay, I'd be like, yeah, that's fair. It's a lot of letters. I ain't gonna lie. So how do I make sense of this in order to not make this, a whole bunch of not letters? All right, let's take a good look here, and let's see what we have. Okay. So to kind of make sense of this, I do want to look at question number 1 here, so that way it does make more sense about how we would approach this type of problem here from a visual perspective. All right. So question 1 says, here's a general curve. All right, here's our generic curve of f of x. And we got here, we got several rectangles of each. I said that's perfectly fine. Now, what is important here as part of this problem is we're going to go ahead and say if this is the region we want to go ahead and do, we want to specifically look at these guys right here. Now, don't worry about all this stuff. I don't even. How do I get rid of this? Always the question. Yeah, I realized that. I gotta seriously remember how I get rid of this junk. Gotta take that off. Oh, not work. Okay. In any case, you know what? I'll just have to work with it. All right. In any case, I want to take a look at how many rectangles that we have here. Now we have 1, 2, 3, 4, 5, 6. We have like 6 rectangles here. Now, I think we have 6. So we have 1, 2, 3, 4, 5, 6. Yeah, we have 6 rectangles. You notice at the top we have 6 numbers on top. Okay, and you notice here we do have a width for each one of these. Notice it goes 1, 2, 3. And wherever these lines are, so let's take a look here at 1.9. All right, where this 1.9, that's the first number that we see here on the picture. All right. And we want to take a look at the width of that rectangle. So we say, okay, well, what's the width of that rectangle there? Well, the width of that rectangle here is from 1 to, looks like 1.25. Oh, that's not it. Let's see, what is that? Looks like it's broken up into 3 pieces. So it looks like from 1, so the first rectangle here looks like from 1 to 1 1/3. It looks to be that way. First rectangle here. I'm looking at that right. Make sure about that. Yeah, that's correct. Okay. So the first rectangle goes from 1 to 1 1/3. All right. That's essentially what it does here. So what's the width of the rectangle? Well, the width of the rectangle here is going to be 1 1/3 minus 1, which is just 1/3. Okay, every single rectangle that you see here is going to be 1/3 units. Okay, that's what we want to have happen here. So we have 1/3 here as what we have here on the outside. That's the width of every rectangle. So again, remember that the formula here for a rectangle is base times height. So we have the base here for every rectangle that we want to go ahead and find the area for. We'll always have a base of 1/3 units. Okay, so that's why we can just put 1/3 on the outside. Now, the height of each one of those rectangles is different. However, the height of each one of those rectangles is defined by the y value of this function here according to the picture. So according to the picture here, the first y value, so from 1 to 1/3, 1 and 1/3 I should say, the first y value is going to be 1.9. Then we add that to the second y value, so that's 1 and 1/3 to 1 and 2/3. That's going to be 1.5. And that's the y value. Again, we're just taking a look at the y values here. Then we go 1 and 2/3 to 2. That's going to be 1.8. And you could probably guess where this is going from this point. So we had 2.4, 2.7, and 2.5. So that's all we're going to do here, and put this in a calculator. We're going to figure that out. I'm going to go ahead and put that in really quick. So if we add these together here, we get 12.8. So we multiply that together times 1/3. So here we get how many 2 decimal places? So we get 4.27 is what we get here. Okay. You can use a calculator for that part there. And so that's what I get for that one. So you're like, okay, that's a picture. All right, so you're probably saying, okay, you know what, that's fair. That's a picture. But how does it work if I have a function? Okay, let's take a look at a functional example. Let's see how that works. So that'll be number 3 here that I want to show off as well. So how does it work with a function? So let's read this off carefully, and I'll show you how this works as a function. Okay. So first and foremost here, let f of x be equal to x squared, and compute the sum of the Riemann sum of f over the interval 5 to 7, choosing the representative points to be the midpoints of the subintervals, and using the following number of subintervals n. They'll give you different amounts. So we're given a function here, f of x equals x squared, and we are having a guy here from 5 to 7. Now, something that is also very important in this problem is the representative points are the midpoints of the subintervals. Okay, so I want to use the midpoints of the subintervals. Excuse me. Okay, well, I'm going to come back to this. So let's do letter A, which says what happens if we have 2 subintervals. Okay, so let's say n is equal to 2. Let's see what we do for that. So the first thing that we're going to do is, if we're going to be able to do this problem correctly with 2 subintervals, the first thing we'll do is determine the width, and then we'll determine the heights after that. So the width here is that b minus a over n. So that's equal to b, this is a, this is b. So b, which is 7, minus 5, which is a, over n, which in this case is defined as 2. So we have 2 divided by 2, which is equal to 1. Okay? So this is the width of every subinterval according to what we want to split. We want 2 rectangles to go ahead and figure out. Fine. Figure out the areas of those rectangles and get the approximate area. Feels fair. So in order for us to actually see those particular values, in order to know what we're going to plug in for this particular formula. Although our width is 1, we need to take a look at the intervals that we'll actually have, and then take the midpoint of each of those subintervals. So if you notice here, we're starting at 5. If the width is 1, we just go 1 unit up. So we go from 5 to 6, and starting from 6, we go up to 7. So again, it's a width of 1, 5 to 6, and then 6 to 7. Then we just take the midpoint of each one. So the midpoint here from 5 to 6 is going to be 5.5. And the width here from 6 to 7 is 6.5. So those are the two numbers that we're going to enter in for our x1 and x2. This will be our x1, this will be our x2. Again, the number of x's should equal the number of subintervals. So here we have 1 on the outside times f of 5.5. Where's my writing? Plus f of 6.5. And we just enter those into a calculator and see what we get. So if you do this out, so here we get 72.5 for this. Okay. So that one is pretty simple and straightforward, but do another one here. All right. So let's put 72.5. Okay. So let's take a look at 5 subintervals. Okay, so what happens in 5 subintervals here? So let's say we're changing the game here now. So we change the game and we say, all right, n is equal to 5 now. Same function, all right, but 5 subintervals instead of 2. So what happens in that case? Well, instead, we need a new width. That new width here is going to be 7 minus 5. You still have the same a and b, but we're going to divide it by 5. So we need to go by 2/5 every single time down for each one of our 5 intervals. We'll just go by 2/5 here in this instance. So we start at 5, we go to 5, and we go 5 and 2/5. And then we go from 5 and 2/5, go another 2/5 units, we get 5 and 4/5. And then get 5 and 4/5, and that goes up to 6 and 1/5. There are intervals here, by the way. And then we go from 6 and 1/5, 6 and 3/5. Really rare I use mixed numbers, but at least it drives the point. Alright, then we get 6 and 3/5, and we go up to 7. And after that, you have to find basically after that, you need to go ahead and find the midpoint of each of the intervals you just go in ahead and described. So in this case here, you have 5 and 1/5. This is the midpoint for the first one. Second one here is 5 and 3/5. Next one here is 6. And this is 6 and 2/5. And this is 6 and 4/5. And then you can convert these into improper fractions if you like. 26 over 5, 28 over 5, 6, 32 over 5, and 34 over 5. So if we're going to find the area for this using rectangles, we take the width, which is 2/5, We're now going to multiply it by the function at each one of those values. And add those up together first and then multiply by 2/5. Again, this should give us a good ballpark estimate about what the area underneath the curve is going to be. Okay, let's take a look at what we have here. All right, so we go ahead and figure this out. Here we got, again, let's go ahead and see what we get here. I'm going to kind of, those are rather tricky to get, I ain't gonna lie. Gotta square each of them. That's pretty long, I ain't gonna lie. Well, gotta do it anyway, regardless of how much I don't like it, but gotta do it. Okay, so let's see what we get here. We get 26 over 5 squared, plus 28 over 5 squared, plus 6 squared, plus 32 over 5 squared. Alright, so let's just do that on the calculator here. We're going to do that together. See that on the calculator here together. You guys can get a idea about how to work with that. Do that on the calculator! Okay. So I'll just do 26 over 5 squared plus 28 over 5 squared plus parentheses 6 squared plus, and then do 32 over 5 squared, parentheses needed, 32 over 5 squared plus 34 over 5 squared. We'll put that as a fraction. Get 908 over 5. So we'll have 2/5 times 908 over 5. And let's see what we get here. By 2/5. See if we can reduce it down by anything. I don't know, but alright, so really can't here. 1816 over 25. We'll do it as a decimal here now. I didn't know if we could reduce that down to make it easier. Alright, so 72.64 is what we. And so that's going to be our answer for 5 subintervals. So if you take a look here at the comparison, you get 72.64 here. Back to our problem here for just a moment. So notice if you compare it to the very first one, the answer goes down by just a little bit based on how many subintervals that you choose. So you're going to get closer and closer to your actual final answer once you do more and more subintervals. So a little bit of work here with that, but want to be sure that you guys were clear about how I came up with that. Are there any questions about that? Any questions at all? It is a lot, yes. I know. It's a lot to take in, but I will need to get through this guy here. This one may require just a rewatch, just to kind of go through the example again. I'm going to do one more part with this, and then this will set us up for next time. So there's one more thing I want to do with this problem here specifically. So. Okay. So let me go ahead and show you one thing here, one problem in this particular problem here that I do want to specifically talk about. All right. This is where actually the payoff is going to come around. And that is part D. Let's talk about part D. Part D is the payoff for the next section, okay? It asks, can you guess the area of the region under the graph of f on the interval 5 to 7? Well, what if I told you that we don't have to guess what the area underneath that graph is going to be between the numbers 5 to 7? What if I told you that we can automatically find out exactly what that area is going to be without having to go through the painstaking work of everything that we just done? So we know that what the ballpark estimate's going to be, but what we want to specifically find out is that in math, we want to be a little bit more exact. And that is where this fundamental theorem of calculus is going to come in. Now, I'm just going to introduce it here today, and we'll apply a ton of examples with this tomorrow. But I want to show you what the key difference here between the process of doing the rectangles, and then the process of doing this, which is basically like taking an infinite amount of rectangles and then essentially finding that exact answer. So the way it works is that all we're going to do is we're going to take the integral of the function here. Okay, so if you notice here, we have the integral, we say the integral from a to b of some function, and we take the integral, we take that integral, we plug in b, and then we subtract it from that integral after we plug in a. So if I were to look at the example here, we got an answer here of 72.64, and you're like, wow, that's all right. So you did all that work. You look at all that work. You're like, oh my gosh, that's a lot of work. But I said, you know what? Let's boil it down to something easier. I said, okay, let's take the integral here. Now they give us two numbers here from 5 to 7. So we're going to take the integral from 5 to 7 of the function that they give us here, which in this case is x squared. Now, I'm going to tell you, we already know what the integral of x squared is. The integral of x squared is x to the third over 3. Now, if you recall, we did the plus c's before, okay? We did plus c's before, and I'll give you this reminder here for tomorrow. But these are definite integrals. Now, because we call them definite integrals because we actually plug numbers in for these guys. With definite integrals, we don't need the plus c here in this case. We're going to actually just use the 7 and the 5 here directly and find out what the exact area is underneath this curve at those two values. So we're going to plug in, first of all, we're going to take 7 to the third power over 3, and we'll subtract it by 5 to the third power over 3. That's all we're going to do. Just as simple as that. So as you see there, the process here is much, much faster. So if I did on the calculator here, okay, well, what's 7 to the third? That's 343 over 3 minus 125 over 3. I can just do, again, you can just use the calculator for this. So here we get 218 over 3. And this is our actual exact answer here, which in this case is 72.67. So if you want to know what your exact value is, your exact value that you'll always be aiming for is 72.67. That's the answer here that you will get for letter D by taking this nice shortcut for these type of problems. Okay, cool. Does anybody have any questions about part D here. Again, this is the shortcut that we're going to be using here tomorrow. I think I've basically fried your brains. So maybe even taking a 10-minute break may not have been long enough. Think you guys are probably full in the head for today. So I'll probably just leave it right there, so not to strain you guys any further. So I know your brain hurts today. There's a lot that I had to say, but there's a lot of information that we kind of had to go through. So I know this is a little bit mentally taxing here today, and I apologize about that. But you know, go through the video here. You should be able to get it. Again, I know when we started off with integration by parts, that's tough enough already. So it's a lot to do, and it's a lot to do. This is like the yeah. Admittingly, I agree with you guys. I agree. It's a lot of headache. It's true. Like amongst all the material in this course, this is the meatiest material that you're going to run into. So this is like the biggest chunk of material that really is pretty heavy and really weighs a lot of people down. So without question, this is like one of those times where I would agree with you guys and be like, I wish we were in a 16-week class, and I wish I could just like break this up into like 2 day, into like a week, and we could just go a little bit slower instead of having 8 weeks. So yeah, this is like the big meat and potatoes of this entire chapter is what we're doing right now. Once we get past this part here for 6.3, 6.4, like we did the shortcut here, much faster problems, much easier to do. We did a sample here today. It's pretty fast and simple. Once we get past this, it'll be a lot easier on the brain. I assure you. Okay? I don't mean to make you guys sad, but I recognize that there are things that we have to do. Sometimes we got to do the hard things. All right. Are we okay, everybody? Are you not going to kill me? I hope so. Let's stop here for today. Okay? All right, ladies and gentlemen. All right, ladies and gentlemen, we're going to stop here for today. I'm going to let you relax yourselves. Just take it easy. Okay? We'll come back tomorrow with refreshed heads. Okay? No one is dying except my 2 brain cells to each other doing their... I gotta understand that. Alright? So let's rest and relax tonight. Okay? Digest what I've just said. And then we're gonna come back tomorrow and do things significantly easier. I promise. Okay? Okay. So we'll end off here on a more somber note, but that's okay. Thank you guys for coming on out here to stream today. Okay? I want you guys to relax tonight. Okay? If you don't worry about looking at homework tonight. Just if it's overwhelming for you, that's fine. Just take a night off. Come back to it tomorrow, whatever. Okay? A lot that we did here today. A lot of talking. A lot of examples. A lot of different things going on. Totally understand. So just take it easy. Just take a day off or take the night off. Come back the next day. Try out the homework. Okay? All right. Okay, so that'll take care of it for today, everybody. We're going to come back here tomorrow, and we'll hopefully be doing easier things on the horizon, okay? From here on out. Toughest day today, but we'll get through it. We move, as they like to say. All right. Thank you so much, everybody. We'll see you tomorrow. Have a wonderful night. Relax and enjoy yourself. All right. Take it easy, everybody. And remember, stay safe, stay healthy. But most importantly, just like after today, stay sane. Exactly. Today, that's why my advice is the way it is. We stay safe. Alright. Alright, Liwen, Elizabeth, Emma, Nick, everyone else here in the chat, thank you so much for hanging out here with me. We'll see you tomorrow, everybody. Take care. Bye! Bye, everybody.